Hello everyone. I'm speaking on behalf of a fine group of people back at UPenn, whose names you can see on the first slide. And my talk today will be about how to try to extract more benefit from programmable networks, and doing this in a way that doesn't burden the programmers who are writing these programs or the operators who are running these programs in their networks. Now, before I begin, let me just take some feedback from the audience, just so that I'll know how to modulate the terms I use in the talk. Show of hands, who has used P4? Okay. And who has heard of P4? Okay. Who has had a good lunch? Not enough people. All right, so I will be mentioning P4, but for the benefit of those who might not be so familiar with it, I'll give context, and feel free to ask me to elaborate after the talk. I'd be very happy to. Okay, so I don't need to impress upon this group of people that there is an increase in appetite and attention for programmable networking. This is affecting the degree at which we can examine and change network traffic as it crosses our network. And this has been very evident both in research and also in products over the last decade or so. But one has to be very careful when one looks at abilities, right? Just because something is possible does not mean that it is feasible at scale or at requisite performance. So in this talk, I'll be talking about how we can try to keep these two features in check with one another. And in particular, I'll be talking about how we can go from writing a single Dataplane program. So this is where P4 comes in, right? So P4 is the de facto Dataplane domain-specific language, if you will. And the idea is how to write a single Dataplane program, because we humans, we like to deal with simple things, and then use and leverage automated support to take that program and run it over a possibly vast and heterogeneous network. Okay, so that's the talk goal in a nutshell, and I'll be telling you about why this is important and how we go about working this magic. Okay, and the reason that this is important, in particular and timely, is because currently the way we go about programming data planes, and I'll be giving a bit more context about what I mean by programs. Currently the way we go about this is in a piecemeal manner, kind of one at a time. And we would like to do this coherently for a program, for a program that's meant to execute at a network scale. Okay, so to do this, we're kind of leveraging an idea that has been around in networking for quite a while. This is a kind of a useful fiction of treating the network as one big switch. And in the system I'll be talking about, Flightplan, we're going to be looking at this as one big programmable switch, right? So this is a convenient abstraction to use as far as the programmer and the operator is concerned, but it doesn't go far enough. Just dealing with the distribution aspect is insufficient. So let's look to see why. So the reason comes down to the varied and heterogeneous nature of networks. In particular, we'll be looking at data center networks, hence the topology you can see on the slides, where originally CPUs gave us a rich amount of transformation we could apply to traffic. And in the past decades, people have also looked at other types of parts, such as FPGAs and NPUs. And during the last decade or so, there has been an increased availability of programmable switch ASICs. Now, okay, so we're talking about varied capabilities, certainly about out-of-the-box ease of programming. And this is also matched by varied capabilities. So when it comes to performance, we find that because of the general architecture and when using a CPU, we have to pay a price when it comes to throughput. And this is kind of inversely so at the switch, right? So usually in a programmable ASIC, the level of programmability we can enjoy is far less than what one would expect on the CPU. But conversely, the throughput that one can expect because of that constrained nature of the execution is higher. So let's stand back a bit and kind of take stock of the features we've come across so far. And I think we can look at network programmability as the management of programmable resources, right? So that's, I know management maybe sounds like a far less sexy word than programming, but that is at the heart of what's happening here. And we need to manage things carefully. And as I mentioned earlier on, one of the problems that we have is distribution, because we have a distributed system, so there's no avoiding that. And two other features of the problem are that the system, for better or worse, is constituted from a heterogeneous array of devices. And one of the nice things we could leverage is find a systematic way of using their complementary features, right? So ideally, we want to, from a programming mindset, we want to focus on the logic, right? We want to express what we want to get done. And ideally, tool chains along the way will help us figure out where to do it and when to do it, right? And how to sequence it. So that's the sort of tool chain support that it would be very valuable to have in a network when programming at a data plane programming level. Okay, so there are pieces of the puzzle already, right? So there's languages, there's targets, but these alone are insufficient, right? So we also need a systematic way of using these in a human-friendly way. Okay, so let's look at the goals then, based on the problem that I've described. So one of the goals is to have a bigger synchronization between the ability the potential of the network to be programmed and the ability of programmers to do the programming, and also operators to run those programs in a way that doesn't get them tangled up too badly. Here, the secret sauce lies in automation, right? So we need to find a clever way of using automation to our benefit. We don't want to have programmers wasting their time writing tedious code, which is potentially buggy, right? So how do we find that sweet spot to support programmers and operators? Another thing we do not want to do is we don't want to create a new language. We don't want to make special assumptions about the hardware, because that would greatly limit the uptake of any such proposal, right? So in the system I'll describe, we work with existing languages, existing tool chains, existing devices, and we don't expect others to change their systems for our benefit, right? Because that would not be a realistic expectation. The system I'll be describing has been prototyped for P4, and I'll be showing you some example P4 code, and I'll be explaining it. And it works. The final thing in our final goal is we would like a clean scoping between programming and operation, right? So these are two activities that interact. There's feedback loops between these two. And we would like to to help develop a constructive and productive process during which programmable networks are developed and run. We want to avoid a blame game that can arise about whose problem might have, who might have given rise to problems in network, right? So I think we have an opportunity at working at this level to try to organize conceptually kind of who owns which part of the process. So let me tell you a bit more about what we are targeting. So this is going to give you a bit more context about what I mean by programming. Increasingly, I'm going to give more specific examples, right? So we're going from kind of general ideas to more concrete examples. So you'll see what Flightplan is intended to do and how it does it. So the activity we're targeting is in network computing. And the idea here of what we want to achieve is to treat the network as a programmable substrate. And as much as possible, we want to be able to push logic, be it traditionally network-associated logic, or perhaps even application logic, into the network to benefit some activity, right? So we want to be able perhaps to benefit the network by making it more reliable, make it more performant, and in doing so benefit users of the network, right? So we have a pretty high bar when it comes to the level of programming that we expect. And we implemented 3 in-network functions. So if you like, these are kind of points of reference of activities that can be done over in the network. The first is a forward error correction. So the first is intended to mitigate faulty links by adding redundant information that gets sent across, using which missed packets can be reconstructed. And this avoids having to resubmit the data, and also avoids transport protocols overreacting to the loss of this data. And this is a payload processing task, right? So this unlike other network operations, this actually looks at the whole payload and has to process it in order to generate the redundant information. The second thing we look at is header compression. So this is meant to remove redundant information in order to save channel capacity. And here we don't have to look at the payload, right? So we look at the headers and work out deltas to save space. And the third is an implementation of a cache for memcached. So we implemented a compliant memcached cache. And here the idea is we want to service an application layer concern, which is reducing latency when it comes to getting replies to queries, and reducing the utilization of network resources between the client and the server, as well as reducing the utilization of the server itself, right? So we have a variety of different in-network functions, and used together, these transparently improve the service of the network. These have been implemented to run in an FPGA. So in the case of the first and the third, and the second runs on a programmable ASIC. And we're currently porting it to run in an FPGA too, so to be able to uniformly run these functions on different targets. But these are themselves just building blocks, right? So the arrow pointing to that Dataplane program on the right is that we want to use them in a Dataplane program. We want to integrate the features they offer us within a bigger logic program. So this is where disaggregation comes in, right? So we are going to start with a Dataplane program and then disaggregate it to find out how to distribute and how to utilize these complementary heterogeneous devices. So for this example, I'm sorry for the animation, by the way. Something must have failed over. So for the example I'm going to talk about, we're going to have a network where we have a faulty link connecting 2 switches, and the switch connects a host and an FPGA board. And basically, the main actors in the story are the key value client and the key value server, and we have 2 flows, complementary flows traveling between them. So the placement of the functions, which is where the operator comes in, right? The programmer doesn't really care where things are placed. The programmer just cares about the logic that links things together, is as follows. So we would be carrying out header decompression and compression on the switches themselves, and we can do that because, as I mentioned, the implementation runs on a programmable ASIC. Whereas the FEC, for example, has been offloaded to an FPGA because there is very little to no chance that a programmable ASIC will be able to do this at scale, and at least with current technology. And that is where we do the key value caching and the FEC decoding. And now I'm going to show you our program. And we wrote this in P4, but for simplicity, this is going to be shown as a flowchart. So the logic goes as follows. So this is what the programmer would be thinking, right? I can have FEC control packets. So these are telling me about the state of the network. And using these signals, I might update my knowledge about whether I want to use FEC on certain links or not. Otherwise, if it's not a signal, I want to check if it's encoded. And if it is, I would want to decode it. I'll check if the header is compressed. And if it is, I'll decompress it. And then I'll check if it's memcached query or reply. And if it is, then I'll put it through the cache. And then I do what the switch does, which is take a forwarding decision. And then the egress logic kicks in, right? So complementarily, I will compress the header if I have to, and I'll do the FEC encoding if I have to before emitting the packet. So this is, so now we're going to look about, so we've seen the whole program. Now we're going to look about how to go about doing the disaggregation.
Can I have one question?
Sure.
What's the point of moving the FEC to a programmable ASIC while all the service blocks already do this for us? What's the benefit?
All right. So this is in relation to the particular FEC we implemented, right? So that's true. So in modern versions of Ethernet, you already have FEC working at the physical layer. However, that is designed to tolerate some limited environmental factors that arise because of the level at which the physical layer operates. If you have loss because of transceiver or link issues, maybe the laser might be dying or the glass is bent too much, that FEC is not going to help you. So you need a more ambitious form of FEC to help you with that. So when we were designing this, we thought, well, we could also we could strengthen the FEC in the link in the physical layer, but then we've changed Ethernet, and we didn't want to go in that direction, right? So that's why we went to the lowest layer at which we wouldn't have to break a standard, which was at the link layer. Okay, so now I'm going to talk about, okay, we've seen a practical problem and the building blocks of it, and this points to a general problem, which we call Dataplane Disaggregation. And I'm going to give you a taste of this, but I'll be very happy to answer questions, and also take things offline if there isn't enough time. So we have the same network as before, which might be an instance of a network which we are more familiar, but we can use abstraction as our friend, and we are going to look at the network as consisting of a composition of programmable data planes. And these are programmable to different extents, and these are data planes that afford us different resources in terms of memory, in terms of predictability. So how can we leverage this for Dataplane disaggregation? And the story goes like this. And this is what we want the programmer and the operator to experience to solve this problem. We start with a single program, and this is an example of which I gave you earlier. And the programmer or tools on the programmer's behalf will logically segment. So in other words, they're going to, I'll show you an example of how this is done. They're going to bunch up parts of the program in a way that is sensible for what the operator wants to achieve, or the resources the operator has available, or their proximity, right? So these are typically very topological features. And then tool support will take the program, break it up, and also stitch together and generate code which will have these different parts of the program be able to interoperate. In other words, it's going to, for example, bunch up states that the program will need when control flow moves from A to B. And that is exactly what's happening, right? So we have control flow moving within the program, but this is being mapped to data flow or network flow within this architecture, right? And here we use vendor-specific tool chains to do the mapping to the hardware, because there is no other way, right? You have to use the vendor-specific tool chain. But for the first bit, for the splitting, you're still dealing in terms of P4 programs. So our tool, which consists of an extra pass in the open source P4 compiler, takes a P4 program and generates multiple P4 programs. And these are cooperative P4 programs, right? So the model is that they will run concurrently, and they can interact to pass along to continue the computation from one to another. And then there's a very important role for the network controller, of course, which is carries out linkage. So in other words, it tells A how to reach B and A how to reach C. And you can also pre-link in case B becomes unreachable. You don't want to have to wait until something else external to the system notices. A will already know how to reach a replica of B in advance. We also have a story about how to monitor and react to the integrity of the program. In other words, we went from having a single program to a distributed system, but that comes with the joys and terrors of running a distributed system. Part of it might become unavailable or might start lagging, so we have a very simple scheme to be able to monitor this program integrity at scale and take corrective action if it lags. Okay, so based on the example I gave you earlier, what would this look like? Well, for a very simple example, let's just think we want to offload the FEC decode part, right? So this would consist of a pretty simple program transformation where we, instead of calling the FEC, we emit the packet with extra contextual information going to the target that can carry out the FEC decode step, and then have it return the result so that the logic can continue where we left off, right? And this is a very simple program transformation. The gathering of states is done statically, and it's a very straightforward data flow transformation. And this can be done, since it's straightforward, it can be done automatically. And this is also why we don't want the programmer to have to deal with this, because it's kind of boring and error prone, so we can spare the programmer from doing this so they can do more interesting things instead. So we can also, naturally, we don't have to offload just individual blocks. We can also offload bigger subprograms, as in this example here, where we have what you would expect to get, right? So you have part of the program gets chopped off and put into a complementary program that's running in parallel, and there's a simple mechanism for these two to interoperate. Okay, so now let me get to how we go about implementing this. So we have a system called Flightplan, which is implemented as an extension to the standard P4 compiler. It's implemented in the front end of the compiler, right? So it does not know about vendor-specific information, doesn't need to know about vendor-specific information, right? It's carrying out this very simple transformation that I just described. And it presents an interface to the programmer, which I'll show you next, an interface to the controller to do the relinking, and generates code for the handover between data planes and gathering the state and transferring it over and doing this program integrity preservation I told you about. So how does this look like to a programmer? And this looks like this. So this is a P4 program. It doesn't do very much. So if you know C, you can pretty much read this. So we declare some state, and the provenance of this state can be obtained from the packet or from other contextual places. We can call functions. These might be P4 functions or external functions. For example, the FEC would be an external function, since the FEC encode or decode are not the P4 definable. We have branching and calling more functions. And to a programmer, a P4 programmer, our interface looks like this. You declare an arbitrary number of flight points. So now we're going to describe the logical segmentation, right? So these are the logical parts that we'll be segmenting to. And then we have this function called fly_to, which instantiates the dotted line I showed you in the earlier diagram, right? So this is what separates one part of a program to another, and this is a P4, it appears as a P4 function. So we can put it anywhere inside branches, right? So it can appear very flexibly inside the code. And this is not P4 definable, so the P4 compiler just looks at it as it's a declaration, right? And our pass will interpret it. So this is interpreted at compile time. And if we want to compile this program as a single program, using a compiler, we'll simply ignore these fly_tos. But if we want to split it, then they will be interpreted to split the program into a topology, which is this is the example of the topology we get. And the analysis will also gather variables in case they are declared in one part of the program, which might be mapped to one physical target, and used on another physical target, right? So we need to make sure that the information will be there when it's needed. Okay, so let me just quickly talk about evaluation. I'll give you a taste of the micro benchmarks we carried out, but I'm happy to go into more detail afterwards. And this is the example code we'll be using. So it's a very simple program. We declare some states, and then we increment it after doing a flight to. Flight start is like our main, our entry point, and then we have alpha carrying out there. And this is our experimental setup. So this is in a single programmable switch. And what we're doing here is we want to find out how a program reacts to being distributed, because this program is no longer running on the same scrap of silicon. It's now running on 2 scraps of silicon, potentially, and separated by a shared link, right? So this is going to give us an idea of what to expect as far as program execution is concerned. And the first thing I'll talk about is handover time. So handover time is, as you might expect, the time it takes for the action to move from flight start to alpha, right, for one part of the program. And what we notice is that, so we tried this, we experimented with different degrees of network utilization and different burst sizes. And what we notice, at least in this setup, we're currently carrying out a more extensive evaluation. What we notice is that the handover time in both cases happens within an order of a microsecond or so in the majority of cases. But as you might expect, there is the effect that's held of increased utilization and increased burst size. The other thing I wanted to show you is program integrity, which is how quickly can we notice that something has gone wrong and therefore react to it. For example, alpha might no longer become available or might be overwhelmed, and we don't want the program to half run, right? So we want to be able to take corrective action there. And the picture here shows that basically we can tune a threshold T so that it is basically the in-flight packets that would be lost. So we implement a transparent disaggregation here, and the functions that I mentioned earlier are transparent, the FEC, the cache, and all that, right? So it is really incumbent on the application or in the transport protocol to manage reliability. So we don't try to replicate any of that here. So there is a whole lot more that I can talk to you about, but I think I'll stop here to take some questions. And should there not be time for enough questions, I'm very happy to talk offline, or that's where you can reach me by email. Thank you.